Welcome back everyone. In this lecture I will complete the proof of complete reducibility. So, let us recall what we have done before. So, we proved that any unitary representation is actually can be decomposed into a direct sum of irreducible unitary representations. So, any finite dimensional unitary representation of G. So, where G is finite group, so can be decomposed into a direct sum of irreducible unitary subrepresentations. So, this is what we proved using induction in the last class. So, now the real question is given finite dimensional representation, how to make sure that that is indeed equivalent to a unitary representation. So, if we prove that then since unitary representation enjoys this property. So, if it is equivalent to some other finite dimensional representation, then that also will be direct sum of irreducible subrepresentations. So, let us state and prove that result. So, this proposition says any finite dimensional representation of G, of course finite group, is equivalent to a unitary representation. And since unitary representation is a direct sum of irreducible unitary representations, using the equivalence we will get that any finite dimensional representation is isomorphic to direct sum of irreducible representations. Okay. So, that part I will leave it to you. So, now I will actually just check that any finite dimensional representation is equivalent to unitary representation. So, let us say phi is the given finite dimensional representation GLV. So, now assume that the dimension of V is n. So, now what we can do, we can actually fix a basis of V. So, fix basis B of V. Now, using this basis we have this isomorphism from V to Cn. So, this is an isomorphism. So, this is just a vector space isomorphism. So, now given this data we are going to actually use this isomorphism to define the action of G on Cn by pulling back the action of G on V. So, how do we do this? So, we can just use the diagrams. So, we have V and then given element G in G, we have the action on this V given by this phi of G. Now, we have this isomorphism between Cn and V. So, now in order to actually get the action of G on Cn, what we can do? We can just simply trace these maps. So, we take first T inverse and then go to use phi G and then we come back to Cn again. So, that actually defines this new representation. So, call it rho, which is a map from G to GL of Cn, where rho of G is defined to be T phi of G T inverse. So, this is how we actually pull back the action of capital G to this Cn. Now, because this is actually done using this fixing the basis, that means fixing the coordinates. So, these two representations are by definition equivalent. So, now we have a standard inner product on Cn. So, let us call that standard product. So, this is the standard inner product on Cn. So, now this standard inner product actually makes Cn as inner product space. So, now what we will do? So, we will use this standard inner product and use the averaging trick to get G invariant inner product on Cn. So, the G invariant inner product is defined to be you will just average this the standard inner product that we have it on Cn. So, we want have this G invariant inner product. So, for that purpose all we do is take all possible images of V and W under the map rho G and then take the respective inner products and then sum it over all elements G and G. And it is easy to prove that. So, this is going to be inner product and this is also G invariant. So, once we prove this, then we have actually G invariant inner product on Cn. So, now it is easy to see that with respect to this inner product, this rho becomes unitary representation. So, let us check this. So, first let us check the property of inner product. So, we want to actually see that it is linear in the first coordinate. So, if we take C1 V1 plus C2 V2 inner product with W, then it's going to be by definition you apply rho of G on. So, maybe let me use this dot notation. So, we use rho of G of V is nothing but G dot V. So, then this is going to be exactly G dot C1 V1 plus C2 V2 comma G dot W where G in G. So, where the right hand thing is standard inner product. So, then this is going to be equal to, because G action is linear. So, this is going to be equal to summation G in G, where we can take C1 out and then G dot V1 comma G dot W plus C2 G dot V1 G dot V2 comma G dot W. So, by using the linearity of the standard inner product we get this. So, now it is clear that we can again take the sum inside by fixing this. So, okay. So, this is okay, sorry, this is just by definition of the average sum. You can see that we can take this scalar out, then this is going to be exactly the inner product between V1 comma W with respect to this new inner product plus this is C2 V2 comma W with respect to the new inner product. So, just by expanding the summation and using the definition, we immediately get that this new inner product is indeed linear in the first variable. So, now let us verify it actually satisfies the skew symmetric. So, if we take W comma V, so then this is going to be again by definition sum over G in G, G dot W G dot sorry G dot W comma G dot V. So, then now using the skew symmetry of this standard inner product. So, you get that this is G in G and G dot V comma G dot W bar, and now the bar under summation commutes. So, this is exactly equal to V W bar G. Okay. So, now what happens if we take inner product V comma V over G. So, then this is exactly equal to summation G dot V G dot V G in G. Now, since the standard inner product all inner product u comma u is always non-negative. So, that would imply that this is non-negative. So, now since each term here in this sum, these are all non-negative. So, that means if this inner product with respect to G is 0, that would imply immediately that the inner product G dot V comma G dot V is 0 for all G in G, because all of them are non-negative terms. So, that would imply that immediately V comma V is 0, and that would imply that V is 0. So, that means, so again this is again goes in other ways as well. So, that means the inner product V V with respect to this new inner product is 0 if and only if the V must be 0. So, that actually verifies that the new inner product that we defined is indeed inner product. So, now we will just verify that it is indeed G invariant. So, that means the representation that we have is actually unitary representation. So, recall rho is what we are interested in, which is actually defined from G to GL and C. So, where this we want to verify that rho is indeed unitary representation. To do that, so we pick some h in G and then we want to verify that this rho h applied on V and then W, the inner product of this is same as the inner product of V comma W, and this is true for all V W in G. So, this is what we need to prove. So, to prove this, so this is the claim. So, to prove this, let us compute what is there on the left hand side. So, the left hand side is, so this rho h V, rho h W G, which is by definition summation. So, let me use again the dot notation. So, G in G where G is applied to this h dot V comma G applied to this h dot W. So, this is the standard inner product. So, then this becomes exactly equal to summation G in G, G h applied on V inner product with G h applied on W. Now, again back to this original thing that the set coset corresponding to h, that is G h G in G, is going to be exactly equal to G. So, that means this is going to be exactly the inner product V comma W G. So, this proves that if we apply a h on these vectors and then take the inner product, that is going to be the original inner products. That means the inner product is G invariant. So, that means the action is indeed unitary action. So, all the elements rho h live inside U n of C. So, this proves the resulted representation C n that is indeed actually unitary representation. So, that means the original representation is equivalent to a unitary representation. So, now as an immediate corollary, you can see that any representation non-zero representation must be either irreducible or decomposable. So, this is a immediate corollary. Any finite dimensional non-zero representation of a finite group is either irreducible or decomposable. So, like I said earlier, if you have equivalent representations, then they behave exactly same. So, if one is irreducible, then another one is irreducible, again one is decomposable, imply that another one is decomposable. So, now it is easy to prove this Masquet theorem. So, which says that every representation, finite dimensional representation of a finite group is indeed completely reducible. So, let me state this as a theorem. This is indeed very important theorem which uses all ideas from linear algebra. So, this proves that any finite dimensional representation of a finite group is completely reducible. So, that means it is a direct sum of irreducible sub-representations or isomorphic to direct sum of irreducible representations. So, let us prove this. So, if we start with a representation V, so this is let us say finite dimensional representation of G, G is finite group. Then from our earlier corollary, V is either irreducible or decomposable. If V is irreducible, then there is nothing to prove. There is nothing to prove. So, assume that V is not irreducible. So, assume that V is not irreducible. So, that means from our corollary we can immediately see that this is V is decomposable. So, that means there exist non-zero sub-representations, let us call it W1 and W2. So, non-zero sub-representations of V such that V is equal to or even isomorphic to W1 direction W2, but we can just take it to be sub-representation. So, they are equal now. So, now what happens, the dimension of W1 and the dimension of W2 both becomes strictly less than the dimension of V. So, now using induction we can actually get the result. So, using induction on the dimension of V, we can get that both Wi are actually a direct sum of irreducible sub-representations. So, now irreducible sub-representation of Wi must be irreducible sub-representation of V. Now, if you collect them all together, so write for example, W1 as some U1 direct sum etc., some UP, and then W2 as some X1 direct sum etc., some XQ. So, then V becomes exactly. So, all these UI Xj's are irreducible. So, then V becomes exactly U1 direct sum etc., direct sum UP, and then direct sum X1 direct sum etc., direct sum XQ. So, now from this we can conclude that V is indeed a direct sum of irreducible sub-representations. So, this actually completes the proof of complete reducibility. So, now one can ask the following uniqueness question. Okay. So, let me post it as this uniqueness question. So, we know that from this complete reducibility that any finite dimensional representation of a finite group is a direct sum of irreducible representation. So, let us say V is V1 direct sum etc., direct sum Vn. So, now what is the guarantee that the representations irreducible representations that appear in this decomposition, they are unique. Okay. So, of course, one talks everything up to isomorphism. Suppose if you decompose V into direct sum of these Vi's, where all these Vi's are irreducible, and then if you decompose V into direct sum of some other irreducible representations. So, then now the question is whether these components Vi's and Wj's are they isomorphic up to permutation. Okay. So, that actually kind of poses the question about uniqueness. So, basically the question is, so whether the number of components are they equal. In that case, does there exist sigma in Sn such that this Vi isomorphic to W sigma I for all I ranging from 1 to n. So, up to permutation and up to equivalence of representations, whether these components Vi's are they isomorphic, sorry, are they unique or not. For example, in the Jordan canonical form, we have actually observed that the Jordan blocks that appear in the Jordan decomposition, so they are actually unique up to permutation. So we are asking almost a very similar question here, and indeed we will prove that later using this character theory that this is indeed true. So, actually one can prove somewhat similar statement even for the general associative algebras. Actually, that is what called Krull Schmidt theorem. Actually, Krull Schmidt theorem guarantees that the decomposition that we have for any finite dimensional representation of associative algebras into indecomposable representation. So, that decomposition is unique up to reordering and isomorphisms. So, such powerful theorems are there even for any finite dimensional representations, but so that actually the proof of that theorem is bit involved, that uses density theorem and so on. So, but here we will see that in this course, so we can prove somewhat similar theorem in this category of finite dimensional representation of finite group using some basic linear algebra, indeed using the character theory. So, maybe just I will state the uniqueness for the associative algebras, but I am not going to prove that. So, if you start with associative algebra, and of course, V is finite dimensional representation. So, we already proved that V will be isomorphic to decomposition of indecomposable representations. So, all these Vi's are indecomposable representations of capital A. Now, as before, we can ask a similar uniqueness question, whether the components these Vi's are they unique up to reordering and isomorphisms. So, suppose if we have other way of decomposing W1 etc. direction Wm, assuming that all these are indecomposable representations of A, then this Krull Schmidt theorem guarantees that, implies that n is the number of components are same and there exists sigma inside Sn such that this Vi always isomorphic to W was sigma I for all I from 1 to n. Okay, so this is even true in this much generality, but like I said, I am not going to actually discuss in this generality. Okay, so before actually getting into the character theory, so let me actually make some observation about general representations. So, we will actually define what is called a fixed subspace. So, that is actually indeed invariant subspace. So, that is going to play an important role in later in the character theory. So, let me just define and then prove some basic facts about it. So, let us fix a representation, call it V, and this so basically we have the action of G on V. So, we are going to talk about fixed subspace with respect to that action. So, what is fixed subspace? So, by definition, as the name suggests, so this is going to be those vectors from capital V that are fixed by the action of all elements of G and G. Now, since fixed space actually nothing but intersection of these eigenspaces corresponding to the eigenvalue 1 for all these operators phi g. So, you can see that this is indeed a subspace. So, this is a subspace of capital V. So, that is immediate. So, but what we claim now that this is indeed a sub representation of capital V. So, V g is a sub representation of capital V. So, recall, so we actually talked about the standard representation of Sn. So, this Cn, let us recall that this Cn is the standard representation of Sn. So, there the Vg becomes indeed the subspace spanned by this E1 plus etcetera here, because we want some vectors that are fixed by all elements of G, and it is easy to prove, maybe you can take it as exercise, that in the standard representation that this one dimensional subspace E1 plus etcetera En is nothing but the fixed subspace. So, let me just verify this quickly and then stop. This Vg is sub representation. So, let us take a vector V in Vg and then element G in G. So, we want to prove that this G dot V is again in G Vg. So, that means let us take some group element H in G. So, and then apply this H on G dot V, then you can see that this is exactly H G dot V, and which is exactly V, as this H G again belongs to G. So, that implies that this H dot G dot V is V for all H in H, and that implies that G dot V is again element of Vg. So, this proves that Vg is indeed a sub representation. So, now as before, if we are working with this unitary representation, we can talk about the orthogonal complement of this Vg, and if you so like I said, we can always start with some inner product and use the averaging technique to get the G invariant inner product. So, if we fix that G invariant inner product, inner product on this capital V. So, you can see that we can talk about the orthogonal complement of this Vg. So, in particularly, so like in the standard representation of Sn, this any representation V can be decomposed into Vg and then direct sum of Vg perp. Now, since the elements of the group G acts as identity on this Vg. So, this Vg as irreducible representations can be decomposed into one dimensional irreducibles. So, this is direct sum of one dimensional irreducible sub representation. So, we can just simply decompose, because the entire action of G on Vg is just identity. So, that means if we are interested in decomposing this V, then we have to focus on this orthogonal complement. maybe later we will see some examples how to actually get decomposition of V into irreducibles. Okay, so indeed, so we have this following interesting projection map. Maybe I will just write down the map. I will leave it to check it is indeed a linear map. So, you have this projection map from V to Vg. So, this Vg does not need to be non-zero. So, it could be 0 also, but using just the abstract definition you can see that we can simply take the average sum. So, given a vector, so you can apply all possible elements of capital G and then you can average them over G, then the resulted element, this is going to be always element of Vg. And we will prove some properties of this this projection. So, basically we will prove that this is indeed a projection. So, this is indeed a projection, and in particularly V can be written as the kernel of P phi plus Vg. So, this is indeed the decomposition that we are interested in, and one will be able to prove that this is indeed a G invariant map. So, this is indeed a homomorphism of representations. Okay, so I will stop here and I will continue with the proof of all these things in the next class.